So we just thought about an exhaustive search algorithm for finding the shortest path in this graph, the shortest path that takes us from the starting green node to the terminal red node. And we found that the exhaustive search is exponential in the number of stages in this graph, right? It's exponential in the number of times where we're forced to make a decision. Okay, so enumerating all the paths and going from there is not likely to be a good choice. So how can we go faster in finding a path in a way that doesn't require us to actually enumerate all the paths? And so, if you're ever thinking about going fast, about solving a computationally challenging problem fast, one of the very first things you should think about is a greedy algorithm. And the reason you should think about it is that it's simple, right? It's an excruciatingly simple approach to optimizing something like this. You shouldn't expect a greedy algorithm to give you the optimal path. Occasionally it will, which we'll see in a few weeks. But at least you should expect the greedy algorithm to be fast. So let's think about what a greedy algorithm looks like for something like this. So here's our algorithm attempt number 2. So a greedy algorithm. So there's multiple ways of thinking about greedy algorithms, and it's not always completely obvious which is the right place to start. But for this one really simple place to start would be to say, hey, let's just begin somewhere. Let's just start here at the beginning. And then at the beginning, wherever we're sitting, we will look at the edges that are in front of us, and we'll take the one with the lowest cost, right? We'll take the one with that in one step that increases our total cost the least. Okay. So what's the first greedy step? Well, from stage 0. So here let's keep a record of what our greedy algorithm is doing. We'll also draw it on the graph, but keep a record down here. So at stage 0, our greedy algorithm sees a 1, a 2, and a 3, and it wants to pick the minimum cost, so it picks the 1. Or picks the one that costs 1, and the decision that it can make that incurs a cost of 1 is up, right? It goes to the up node in the next stage. So stage 0, the choice is up, and so we go along here. Okay, so there's our first little rainbow path. Up, and the cost, so here our decision is up, and our cost is 1. All right, so in stage 1 now, having made the choice up, now we're here, right? Now we're in this node. We have 3 choices in front of us, one with a cost of 5, one with a cost of 0, and one with a cost of 1. So let's take the one that increases our cost the least, which is middle, right? It's the one with the cost of 0. So the cost of 0 is this edge here, and that takes us to middle, and it has a cost of 0. So we're doing great so far. We've gotten all the way to stage 2, having incurred only a cost of 1, right? A total cost so far is 1. So things are looking good for the greedy algorithm so far. So now what do we do in stage 2? And now remember, this is the last stage where we can make a decision. So once we're here in stage 2, there's no more decisions to make. And so let's look at our choices. And our next choices to make are 7, 7, and 7. Okay, so we are, as far as we can tell, in evaluating a greedy step, we can't distinguish between any of these. So we can just pick arbitrarily. For example, we could pick. Apologies. There we go. For example, we could pick up, right? Up, as far as we know, up increases our cost by the same amount as middle and down. So we'll just pick up. Okay, because this greedy algorithm is only looking one stage ahead. Right? That's how it's designed. So in stage 2, what do we do? Well, we choose up again. That increases our cost by 7, which is fine as far as we know, right? Because all we know is that there were 3 different choices, each with a cost of 7. And so then once we're up here, well, now we're stuck with whatever cost we have left. Nothing we can do about it, right? We've committed to this edge or this node, so that gives us an additional cost of 4. So I'm going to call this the terminal cost. There's no decision to make, but we still incur a cost. Terminal. There's no decision, but the cost is 4. Okay, so now in total, what's our cost? Well, our total cost for this path, here, let me fill in these nodes here just to make it clear what we've done. So our total cost for this path is 1 plus 7 plus 4, which is 12, right? Total cost is 12, okay? And it was a quick thing to do, right? We have 3 decisions to make, or 3 times where we have to make a decision. At each of those places, we have to choose between 3 different things, right? So that means we have a total of 3 times 3 kind of algorithm steps here. 3 decisions to make, have to do that 3 times. So we have 3 times 3. So our time, and if we want to generalize that, our time is the number of stages to make, just times, right, multiplied by the number of choices that exist at each stage. So here it's the number of stages times the number of choices per stage. Right? And so this is linear in the number of stages, right? So if we have n stages, this is some number times n. Okay, so this is linear in the number of stages, which is a lot better than exponential. Okay, so that's a good sign. Okay, but did it give us a good path? So we said the total cost of this rainbow path is 12. So we can ask, is that the best path we could have chosen? And I hope it's obvious that it's not, right? Even in the last stage there, what we should have done is gone middle instead of gone up, right? So I can switch from from up to middle in the last stage and reduce our cost by 1, right? So here's a path, this red path goes up here, down here, and then stays middle. You can't read that at all. Rewrite that in there. Okay, so it goes up, middle, and then middle gives us a cost of 11, right? So up, middle, middle has a cost of 11 total, instead of the 12 that we got with the up, middle, up, okay? And so, you might say, well, look, the greedy algorithm, it could have found that middle one. Of course, the greedy algorithm could have found a better path than it found, but it didn't, right? Because of the way we happen to set things up and because of the tie-breaking rule we used at the end, the greedy algorithm found a path that wasn't the optimal cost. It found a path that had a cost of 12 that we know just by looking at that last decision that there is at least a path that has a cost of 11. In fact, 11 isn't optimal either. Okay, optimal here is something considerably better, right? So, for example, see if we'd gone up and then middle. So if we went up and then middle, and then middle, that would have given us a significantly better cost, right? Of 2. Well, that's 12. It's 12 as well. Let's see. So, that would be 11 as well if we'd gone up. This is up, middle. Find my optimal path. We'll get the optimal path in just a second here. So this is part of the challenge of this problem, right? Is that it's not obvious just looking at this what the optimal path is. Anyway, the point is, the greedy algorithm could have found something better, right? In fact, here it could have found something with a cost of 11, but it didn't. So that means the greedy algorithm, though fast, is not guaranteed to give us the optimal path in the graph. Okay, so it's fast, but this is not optimal. Right? There exist paths in the graph that are better than the thing that the greedy algorithm returned to us. So that leaves us with the question of how do we actually solve this problem, right? What's something that's faster than exhaustive search, but guarantees optimal solutions, unlike greedy? And can we go as fast as greedy, or do we have to take some kind of a speed hit compared to greedy just to get optimal?